Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now. So Arnav, the butterfly effect. You know, the idea that a tiny cause like the flap of a butterfly's wings in Brazil can lead to a massive effect like a tornado in Texas.
Yeah, and that idea actually comes from a scientific paper published almost 50 years ago. It's probably one of the most famous modern scientific concepts in pop culture. And the example that you took is like just a textbook example, like butterflies wing in Brazil and tornado in Texas. Yeah, fair enough.
Yeah, I checked IMDb and there are like, I think 61 movies, TV episodes and short films with the words butterfly effect in the title. Not to mention all the references in movies like Jurassic Park and all the songs, books, memes. It's just endless.
Oh, memes, yeah. But 61 is crazy, bro. 61, just in the title is... Okay, fine. But the reason people are so fascinated by it is because it taps into this deeper question of how well can we actually predict the future, which is like deep.
Right, because if you go back to the late 1600s, Newton's time, everything seemed damn predictable. He came up with his laws of motion and universal gravitation, and suddenly we could explain the motion of all the planets and moons, predict eclipses centuries in advance.
And then came Laplace or Laplace. French physicist Pierre Simon Laplace imagined this super intelligent being called or nicknamed Laplace's demon that knew everything about the universe, like in the current state, like the positions and the momenta of every single particle and how they interact.
Yeah, and if that intellect was vast enough, it could analyze the data and basically see into the future, which is what we call as complete determinism. It is the idea that the future is already fixed. We just have to wait for it to happen.
And if you know a bit of physics, that kind of feels like the natural way to see things, right? Sure, there's Heisenberg's uncertainty principle that says that there's intrinsic randomness in the from quantum mechanics, but that's only relevant at the atomic scale, not something that affects our lives like as significantly as we might think.
Exactly, because most of what we study in physics is predictable and big, right?
Yeah.
Motions of planets, falling objects, and pendulums. But that's not always the case, though.
Yeah, let's just take the Earth and the Sun, okay? Two bodies interacting is straightforward enough. But the moment you add like a third body, the Moon, everything changes. Like, this is the three-body problem, which we've spoken about earlier, right? So, it just becomes vastly more complicated.
Yeah, Newton himself struggled with this. He once admitted to his friend Halley, the Halley's Comet guy, that trying to calculate the moon's motion gave him such a headache and kept him awake so often that he finally decided to stop thinking about it altogether.
Well, the problem, as Henry Poincare would discover 200 years later, was that there was no simple solution to the three-body problem. He had actually glimpsed to what we now call literal chaos.
Chaos really came into the focus in the 1960s when meteorologist Ed Lorenz tried to build a basic computer simulation of the Earth's atmosphere. He used what we now know as 12 equations and 12 variables of Lorenz, things like temperature, pressure and humidity, anything you would expect
For the weather prediction,
forecast. Yeah. And the computer basically printed out a sequence of numbers showing how these values evolved over time.
And the breakthrough came when Lorenz wanted to rerun a previous simulation. So instead of starting from the beginning, he just took a shortcut. He took like from the halfway point and he entered the numbers from halfway through a previous printout and let the computer calculate from there.
Yeah, and after basically grabbing a cup of coffee, Lorenz returned and he was stunned. At first, the new run closely followed the original, but later it started to diverge. And before it was long, it was predicting completely different weather.
And his first thought was, bro, the computer's broken. Like maybe a vacuum tube has failed or something like that.
But everything was working fine.
So what was the real issue?
The printer rounded numbers to 3 decimal places, while the computer calculated with 6 decimal places. That tiny bit of difference, less than 1 part in 1,000, caused the entire system to evolve unpredictably.
So then Bros tried to simplify his equation, reducing them to just 3 variables instead of 12 and representing a basic model of atmospheric convection. You can say 2D slice of air heated at the bottom and cooled at the top. Still, the same behavior emerged. Even the tiniest change in initial conditions led to dramatically different outcomes.
And this phenomenon is known as sensitive dependence on initial conditions. It's the hallmark of chaos.
Big words, nice. So, since he was working with 3 variables, we can visualize the phase space of his system in 3 dimensions. So, and we can, say it, it's a visualizable problem. It's not 4 dimensions, right? So, it's fine.
Yeah. So, we can pick any point as the initial state and just watch how it evolves. Does the system move towards, a fixed point or settle into, a repeating loop?
And as far as we know, for the weather part, it doesn't actually seem to. In fact, it will never actually return to the same state again.
And to basically visualize this, we can start...
Think about,
we can start with, say, 3 initial states that are extremely close together. So 3 points that are, very, very close together.
You can say 3 points, 3 parallel lines, each with, a point. Line segments, each 3 line segments, and the starting point of 3 line segments that are all parallel to each other. They all start extremely close together, and at first they evolve in nearly identical ways, basically parallel together.
Correct.
But soon they began to diverge. They're not parallel anymore. Maybe one goes left and one goes right, or different angles or whatever. So what started as tiny differences, maybe it was at 1 degree. 1 degree difference from then led to completely different trajectories after some period of time.
And this is basically sensitive dependence on initial conditions in action. Now, it's important to note here that there's nothing random about this system. It's completely deterministic, just like a double pendulum, if you could say. If you could input the exact same initial conditions down to infinite decimal places, only then you'd get the exact same result every time.
Well, the problem is, unlike a pendulum or your double pendulum, this system is, a pendulum is not chaotic, but...
pendulum is chaotic.
Yeah, exactly. So, unlike a pendulum, this system is chaotic, so any minuscule difference in initial conditions gets amplified, a lot, into a totally different final state.
It seems like a paradox, but this system is both deterministic and unpredictable. In practice, you could never know the initial conditions with infinite precision.
Yeah, because infinity doesn't really exist as a concept in our brains, exactly.
Yeah, and that tiny uncertainty makes a huge difference over time.
And that explains why even with today's supercomputers, not quantum but supercomputers, it's so difficult to forecast the weather more than a week in advance. In fact, they've shown that by the 8th day of a long range forecast, so basically it's fine for the first 7 days, but the 8th day the prediction is less accurate than simply looking at the historical average for that one.
That's why meteorologists no longer rely on a single forecast anymore.
And also that's why that also might be the reason that might be because of global warming, recent years, temperature. 2025 was supposed to be the 3rd hottest year after 2023 and 2024, but right now it's on track to be the hottest year.
Damn.
Yeah, that's just sad.
So, back to what I was saying.
Yeah.
Basically, because of the inaccurate prediction on the 8th day, it's why meteorologists no longer rely on a single forecast anymore. Instead, they use ensemble forecasting, running multiple simulations with slightly different initial conditions and model parameters to generate a range of possible outcomes.
And far from being an exception, these chaotic systems appear all around us. Take the double pendulum that you spoke about 2 minutes ago, right? It's just 2 simple pendulums connected to each other. But despite that simplicity, it's very chaotic, bro.
Yeah, because if you take 2 double pendulums that are released simultaneously with almost identical initial conditions, they will at first follow very, very similar paths, but before it is long, their motions diverge completely. And no matter how carefully you try, you can never release a double pendulum in exactly the same way twice. Its motion will always remain unpredictable.
Now, you might think that chaos only arises in systems with high energy or erratic movement, but even in seemingly simple setups, stuff can be chaotic. Consider a system of like, let's say, okay, fine, fidget spinners. Remember them?
2017.
Yeah, long ago. It's 8 years old, bro. 8 years.
Damn.
Okay, so consider 5 fidget spinners, okay? And each of them, so we'll consider a fidget spinner with 3 like arms, okay? And each arm has a magnet. So at first, and if you keep the fidget spinners in a circle, so 5 fidget spinners in a circle, and you have magnets like in their arms.
Yeah.
So at first glance, it might be like regular, like they're all moving slowly, fine. But if you like actually do this experiment, you'll realize that suddenly one spinner does something else like randomly, unpredictably, and it disrupts a pattern. So like there's no like actual pattern to this. It's all chaotic.
Yeah, even our solar system is not immune to this chaos. I read that a study simulating the solar system's evolution over like 100 million years or something like that.
And that's very less, like it's a very short time scale, right?
Yeah.
Because I think, I don't need to elaborate, but it's very short time scale.
Yeah. It basically found that as a whole, its behavior is chaotic with a characteristic time scale of about 4 million years.
Oh, that's even less. Oh, nah.
Yeah, that means that within 10 to 15 million years, some planets or moons could collide or even completely be ejected from our solar system.
Oh, and you wanted to like crash Neptune and Pluto together, right?
That's just because I thought their orbits were basically overlapping, but then I realized that it was 3-dimensional and not 2-dimensional. Okay.
Yeah, but that's not the point. The point is it can still happen because of chaos theory. You can hope.
It should. I want to see a dhamaka, please.
Yeah, it's fine. So the very system we often see as the pinnacle of order, our solar system, is unpredictable on even modest timescales of 4 million years or 100 million years, whatever, right?
Yeah. So how well can we really predict the future, though?
Well, when it comes to chaotic systems, predicting the future is like a losing battle. The further ahead we try to look at, the harder it becomes, until beyond a certain point, predictions are no better than lucky guesses.
And the same applies when we are looking into the past. Tracing chaotic systems backward to pinpoint its initial cause is just as difficult. It's like trying to peer through an ever-thickening fog. The further we look, whether forward or backward, it doesn't matter, the lesser we can see.
Yeah, looking without any night vision or any technology, just naked eye. So that's just hard, right?
Yeah.
So chaos imposes fundamental limits basically on what we know about the future and what we can infer about the past of any system.
But there is a silver lining to this. Let's return back to the phase space of Lorenz's equations. If we start with a range of different initial conditions and watch them evolve, at first the motion seems completely disordered, but soon we can maybe see that all the points begin to settle onto a specific shape, an object that coincidentally resembles a butterfly.
And that's called the attractor. So for a vast range of initial conditions, the system eventually settles onto this attractor, no matter how chaotic it may have seemed earlier, or it may have seemed like at any point in time.
Yeah, and if we notice something remarkable, the paths traced in phase never cross each other. They never form closed loops also. If they did, the system would repeat itself indefinitely, making itself periodic and predictable. But instead, each path is an infinite curve within a finite space.
One sec. How is that possible?
It's a little something called fractals, but
Yeah, okay, fine.
that's another story for another time.
Yep, fair. And the particular structure which looks like a butterfly is known as the Lorenz attractor, fair enough, because he's the weather guy, right?
Yeah.
Cup of coffee. But perhaps the most famous example of a chaotic attractor is this, though many others have been discovered for different systems of equations.
Most people associate the butterfly effect with the idea that small causes make the future unpredictable. But the science behind it also reveals something deeper, a hidden, intricate structure that governs the dynamics of chaos itself.
And while we can't predict the exact evolution of any single state, we can understand how a collection of states evolves over time, right? And in the case of Lorentz equations, that evolution takes the shape of a butterfly, leading to the name butterfly effect.